All right, welcome to EECS 373, Introduction to Embedded System Design. I'm Lance Sample, and this module is on the serial bus and SPI. All right, so just kind of reorientate us in the course. This is part of section 5, where we're talking about different serial protocols. In particular, we're looking at the SPI interface, so serial peripheral interface. All right. If you're looking for further reading, from the family reference manual, the large reference manual for all the STM L4 chips. Section 52 is all about serial interfaces. You can find details on the operation of this particular module, registers and configuration types, modes of operations, interrupts, all that stuff is there. If you're looking for a little bit more background, just maybe philosophy on serial protocols in general, chapter 22 of this book is good. This information is also all over the web. Serial peripheral interfaces are really well known, and there's some good data sheets and reference manuals from different chip manufacturers. All right, let's get started. So a little bit overview on serial peripheral interfaces, or SPI. It's a common communication protocol using 4 wires. And again, I always remind you, it's 4 wires plus ground. It's primarily used for chip communication. I should say, if you're on a PCB, ground is just implicit. Ground, there's usually a ground plane. So I just bring up the point about ground, just because oftentimes when we're prototyping something in 373, you're trying to go from one little dev board to the other dev board, and if you forget to put ground there, that's when there's a problem. But on a PCB, it doesn't matter. Ground's implicit, it's always there. Anyways, SPI is really good for having a single controller that's talking to multiple peripherals. It's really well designed for that. It's a synchronous protocol, meaning there's a clock, and it's a fully duplex, meaning the transmitter and receiver can both transmit information to each other at the same time. They don't have to, and oftentimes they don't, but it's definitely possible they could do it at the same time. And it's a pretty fast protocol, so you get multi-megabits of data transfer. So SPI wiring, here we can see a kind of a typical case where you might have your microcontroller being the controller of the SPI bus, and it has several connections to all the peripherals. Some of them are shared and some of them are individual. So you have the serial data out from the device's point of view. So here we have serial data out is going to all the peripherals. Serial data in is a bus that goes to all the peripherals out of all the peripherals and into the controller. There's a system clock. This comes from the controller, and it goes to all devices. What's different is the one thing that's not shared signal is a chip select. And so this is a line that is unique to each one. So this is equivalent to P select from the APB bus. Okay. So when a controller wants to select a peripheral, it sets the chip select line low. And here it's just indicated with this bar on top. That's the standard terminology, just to show a bar. But then again, sometimes you don't see it, so it's always good just to look at the data sheet just to make sure. Again, the controller generates the clock, so it's a distributed clock. And this is just another example of shift registers, shifting data in and out over multiple clock cycles. So this is a synchronous and fully duplexed system. So you can think of this as kind of a ring of D flip-flops where data from, in this case, the peripheral is being sent into the controller. So here, data bit 7 goes into bit 0, and then the clock cycle again, bit 0 goes into bit 1, bit 6 into 7, 7 into B0. So basically, every cycle it goes through. But what's also happening on this side is that it's pushing data out through here. Okay, so you're transferring data back and forth. These packet sizes can be either 4 to 16 bits. 8 bits is pretty typical. 16 bits is pretty typical too. I rarely have ever seen 4. If I don't know if I could ever remember it. There's no acknowledgement. There's no flow control or anything like that. Peripherals is important to think about. Cannot initiate a conversation with the controller. The controller always has to use chip select to tell a peripheral, okay, the bus is clear because the controller has defined it, and now it's your turn to talk. So this does create problems if you're trying to have asynchronous events occur. Say something important is happening over here on the sensor and you need to send the data back. That can be a challenge. I will talk more about the shift register idea. It's important to know that's what's underneath the hood, but that's not necessarily how we think about using it when we're transmitting data back and forth, and we'll see that in a minute. Okay, so let's look at some timing diagrams so you get some background here and kind of get some visualization about what's happening. Okay, so we start off with a clock, some clocking edges. In this case, we're going to look at some rising edge, even though the negative edge is denoted. We're going to look at rising edge for clocking data in. Chip select goes low. This indicates the beginning of the communication round for that peripheral. We have the serial data out of the controller into the peripheral, and at the same time, serial data is coming out of the peripheral and into the controller. And here we see, all right, the positive clock edges right in the middle here of this packet. We're going to clock in the data into the peripheral and into the controller for the return path, and then data is changed. It just happens to be on the lower edge. You know, there's no requirement other than you need some setup and hold time, but typically always done on the falling edge. Data is changed, and now you can either be 1 or 0, 1 or 0, each one of these packets. Okay. Now, SPI is pretty flexible in terms of, are you clocking in data on the rising edge or falling edge, and what's the polarity of the data or the phase of the data. Okay, so here we're looking at, let's see, how does this work here? So we're looking at the clock peripheral here, or clocking polarity. So are we going to clock on the sampling edge or the toggle edge? And then this is the clock phase over here. So we're going to look at so we're switch the toggling edge and the sampling edge. And this is, are you going from positive to negative with, or sorry, not positive negatives, but high to low or low to high. So this thing is all rising edge, we could say, and this is all falling edge here. And this is where it's going to be sampled. Is it on the sampling on the falling edge or the rising edge in the positive configuration, negative configuration? Okay. Basically, the thing to take away, and I think I said it backwards 3 times, but the thing to take away here is there's 4 configurations. Is the clock positive or negative? Are you sampling on the rising edge or the falling edge? That's it. And here's just another way to look at these diagrams. Here's where the sampling has occurred, right? And then you have 4 different variants of the clock signal that can occur for that same sampling edge, right? So here, let's look at the 3rd bit here. If you are at polarity 0 and phase 0, that means the signal starts out originally low, and you're going to clock on the rising edge. Counter example here is if your polarity is 1 and your phase is 0, the clock is going to start out high and go low, and you're going to clock on the negative edge. So you can work your way through these diagrams and this diagram to figure out all 4 of those combinations. Let's see. This is, I know I talked about these ring buffers before and the shift registers are shifting in and out. This is the typical case, right? The controller has asked something of the peripheral. It sends over, say an arbitrary command. I don't know what this really does. I don't even know what this case is for, but say you say, get me the sensor data, right? And that's encoded with the ASCII S. And the peripheral doesn't have that data ready yet, let's just say, so it's going to send back all ones. It doesn't matter what the data sent back is, it doesn't matter. It's all ones in this case. And now the peripheral has gotten that command, has had some time, usually defined by the data sheet, what the response time is, but has processed it and now has the response, which is F, right? So now the controller is sending out, again, right, send out these 8 bits to clock data into the peripheral, and now sends another 8 clock cycles. It's not sending anything out in this case. It could if it wanted to, it doesn't have to. It sends out all ones, and here the peripheral is sending back data as ASCII F. So this is just an example that you would typically see for SPI. And then again, the chip select line has gone low. Now, the chip select line didn't have to go low the whole time. It could have come back up and gone back down. That's fine. The chip select line does not change the power state or do anything other to the chip, the peripheral chip, than just tell it when it should talk or not. So you have to look at the data sheet to figure out what the timing for all these signals should be. So should chip select stay low the whole time? Should it come back up? I don't know, but it's based on that data sheet. Okay. So data rate SPI, it's interesting that SPI does not have a defined maximum data rate. There's nowhere in the spec that says this is how fast it can go. This is typically because SPI is a protocol between that you can reconfigure between 2 devices, right? You have a controller and a peripheral, and you could even change the data rate if you go to a different peripheral. So it's not defined by hardware or anything. There's not a hardware limit, right? It's as fast as your hardware can go. So this is done with push-pull outputs, right? This is not a open drain, and push-pull means you can drive current in and out of a bus. And why do you need to do that? Is because buses have capacitance. So if you think about your RC charge and RC discharge, you have a capacitor, you have to get it to 1. You can drive it slowly with some current, it'll slowly give up, or you can drive it really fast and it will go up. So your buses are typically limited by the drive strength of the output stage and the capacitance on the bus. I mentioned this before, but the timing that you need is defined usually by the peripheral. Usually the controller, being a microcontroller, has a lot more flexibility, but your device you're looking at, your gyro, your temperature sensor, who knows what it is, has some specs it must meet, and usually it's a range of clock frequencies which it can accept. There are some standard speeds. I don't know how standard they are, but you look through some data sheets on different websites from different manufacturers, and they kind of all coalesce to a couple of these different ones. So 700 kilobytes to tens of megabytes. This is still pretty rare. Systems I have seen as high as 100 megabytes per second. The challenge becomes, and we talked about it in the trade-offs, is that you're trying to switch that fast, and that creates noise. It corrupts your power lines. It sends data. It leaks information. Maybe the leaking the information part isn't that bad, but it causes RMF, EMI noise that can corrupt other signals. So you have to really want to go that fast. You have to really decide that this is the right protocol for the job that you're trying to do. We talked about what do you do if your peripheral wants to talk to the controller. As part of SPI, it does not have built-in mechanism for that. So many chips, this is an example of a gyro, a 3D gyroscope, they have external lines that will drive over to interrupts for the controller. So imagine you have a gyro that, you know, if it spins so fast, it should throw an interrupt. So then you would throw a line high here, then you would set up a separate interrupt that's independent of the SPI interrupts to raise a signal high, and then that would go, you could when that interrupt goes high, you could say, okay, what's going on? Now it's time to go and check through SPI to check what's going on in the peripheral. So there are these out-of-band considerations you might have to do to kind of trick SPI into getting bidirectional communication. The other one that's often tricky is that say you have a couple dedicated chip select lines built into, you know, the drivers or the module for the controller or the microcontroller that you're building or using, but you need an extra one. And so you want all your drivers to already work and know when to pull chip select low, but you need this extra line. And so it's oftentimes you have to kind of dig into the firmware libraries to add in an extra chip select. If you have, say, more than, you have the standard number of peripherals is 3 for your chip, and then you want to go make it a 4th. It's totally possible. You just need the serial peripheral module to be pulling that line up and down for you at the right time. Okay. We talked a little bit about this. It's just that it leads into an extra interesting ways, this idea here of having shift registers where you can, by writing data into a register, right, writing data in here, you're actually, because it's shift register, you're pushing data over here. So it's kind of like this swap, right? 8 bits, 8 clock cycles go by, and all the data from the blue side has passed into the red side, and all the data that was in the red side has passed into the blue side, right? This idea of shift registers actually becomes pretty powerful when you start thinking about other topologies other than star networks. So here's an example of a microcontroller that has, this is kind of a ring topology where we have the data out of the microcontroller goes into the data in of the peripheral. The data out of the peripheral goes to the next peripheral and to the next peripheral. And then finally the data out of the last peripheral or the nth peripheral comes back around and goes into the controller. So what's happening here is that you're using these shift registers to shift data all the way down through the line of peripherals, and you didn't actually have to have more chip select lines. So that's kind of nice. You especially if you say have 100 peripherals, you don't want to have 100 shift select or chip select lines. So one kind of common place that this happens is RGB LEDs. Because you have a long strip of them, you want them to be each controllable, but you don't want to have to run a chip select to each one or any individual line to them. So you can imagine each one of these peripherals is RGB LED. You put an 8-bit color value in there, or however many bits the data sheet says, so you send it in this one, and then you keep clocking it all the way through. So time period 1, you go and put in value into here. Time period 2, so 8 clock cycles later, you put another variable in or put a value in here. Well, when that happens, the value that's in peripheral 1 gets pushed into peripheral 2. Time unit 3, you send another value out. That 1 goes to 2, 2 goes to 3. Right. So now this is a way to shift them through. What they do with the LEDs is they do it faster than you can see, right? You go megahertz if you wanted. So you just push all this data through, you hold it there, and then all of a sudden all the colors changed before your eyes. So we can take a little look about how that would work. In this example, we have 1 controller and 2 peripherals put up in this configuration. And here we see that this is the input word for U2, which happened first. So it gets pushed into U1. and then you push, oops, come back. So here U1 was pushed out of the controller first, and then the word for U2 came. I think my builds are broken, but it doesn't matter. So U2 goes here, then the next protocol comes in, U2 goes into U1, or U2, the data for U2 is in U1, then in the next packet transition, it goes from U1 into U2, and the value for U1 is put into here. All right, so just fun to think about that ring topology, and that you can do other things with it other than just the star topology that I showed at the very beginning. Okay, so SPI on your STM32 L4, there's 3 of them that have a whole, standard bit of configuration to them. You can have some nice things there that you can have hardware CRCs. So CRC is like a parity bit. It just works a little bit different to detect errors. Each one of these SPI modules has an IRQ for it, so you can set up interrupts for it. The internal buffer size is 32 bits, which is nice. That way you don't have to come back to every single one. You can let 2 or 4 packets come in and fill up. And of course they all have DMA capability. Makes them pretty flexible. Okay. So the pros of SPI, it's a very relevant and standard chip-to-chip communication mechanism. So 4 wires, but it's really 3 plus n, the number of peripherals you have, unless you use the ring modality. It's faster than the asynchronous serial that we saw from your. It's nice because there's no addressing. You just simply raise a line lower or high if you want to talk to a chip, and the reference to addressing comes in to I2C, which we'll talk about next, which does have addressing. The cons, the peripheral, when you want to talk to peripheral, the select line doesn't scale to a large number of peripherals, at least not in the star configuration. And what I mean by star is you have one controller and then multiple peripherals that aren't connected to each other, that stand on their own. Okay? There's no acknowledgement of that a packet's been received or that the device is even on. So you can sit there, and I've done it, where you think you've powered up that peripheral and you're just certain everything's just fine, and you're sending packets over, and you say, well, it got my value to boot up and return a packet, and nothing comes back. So that can be a little painful challenge as you're debugging your devices. And by default, the con of this protocol is that the controller must initiate communication unless you've built in some out-of-band mechanism for the peripheral to wake up or talk to the controller. All right, with that, I'll end this here. The next module is going to be I2C. Thanks.